In this video, we're going to get started with the calculus textbook. So in this textbook, calculus officially starts in Chapter 2. Chapter 1 you can think of as pre-calculus. Pre-calculus just being a review of concepts in algebra and trigonometry that are most relevant to calculus. But there's nothing that you learn in pre-calculus that isn't taught in a full comprehensive algebra or trigonometry course. Again, pre-calculus is just a review of concepts from these subjects that are most relevant to calculus. Okay, and so there are full algebra and trigonometry playlists on this channel. So if you need, you can go through those playlists first and then come back here. Or just as you're going through this playlist, you can reference certain topics, certain videos from those playlists as needed. Okay, so in this video, we're going to go through the opening section of Chapter 2. So where are we starting in calculus? What are we going to learn first in calculus? Well, this opening chapter is titled Limits and Derivatives, but really calculus starts with learning about limits. The first thing we want to do is learn exactly what a limit is and how we evaluate limits in all different circumstances. And the reason is because limits are the foundation of all of calculus. The definition of the derivative, the definition of the integral, and the main concepts that we learn regarding infinite sequences and series in Chapter 11. All of this is based on limits. Okay, but now in actual practice, applying calculus in real-world situations, we don't often explicitly deal with limits much at all. However, again, the underlying definitions, the meanings of all the calculus concepts we do use in real-world situations, derivatives, integrals, etc., are based on limits. So you can't have an intuitive understanding, an intuitive feel for calculus without fully understanding what limits are and how to evaluate them. Okay, but now, so then, why are derivatives included in this opening chapter then? Why not have this opening chapter just be about limits? Well, if you were writing your own calculus textbook, maybe you would choose to not include derivatives in the opening chapter like this. Just have the opening chapter be about limits. However, I think what James Stewart is wanting to do is he doesn't want to just blindly introduce us to limits, but he wants to start by giving us a feel for one of the purposes of limits right from the start. And of the three main concepts in calculus, the derivative, integral, and infinite series, the derivative is probably the simplest to learn. So that's why derivatives are mixed in with this opening chapter. Okay, but now we're going to talk a lot more about derivatives in Chapter 3 and Chapter 4. So we're not learning everything about derivatives here in Chapter 2. In Chapter 2, we're just going to learn about what the derivative is. So the purpose and definition of the derivative. Okay, and so this opening section of Chapter 2, you can see is titled the tangent and velocity problems. And what this opening section is about is it's trying to give us a feel for why calculus was invented in the first place. It's going to give us this feel in relation to the purpose of the derivative. But at the start of Chapter 5, we're going to go through a similar type of section in relation to the purpose of the integral. Okay, so calculus was invented in the 17th century by Isaac Newton and Gottfried Wilhelm Leibniz. They didn't work together, they worked independently, but both are given credit for inventing calculus. Okay, and so we can imagine how prior to calculus being invented, the subjects of algebra, trigonometry, and geometry were already fully developed. Okay, at least specifically, I'm referring to the widely accepted applied algebra, trigonometry, and geometry that non-mathematicians are most familiar with today. So what I mean is, like, for math majors, algebra, as we know, gets a lot deeper than what we as non-math majors are familiar with, right? But like the algebra, trigonometry, and geometry that we learn in high school in what's taught in a fully comprehensive college algebra or college trigonometry or college geometry course, like the playlist on this channel, you can think about how prior to the invention of calculus, these subjects were already fully developed, okay? But even with these subjects, there were still math calculations that were inaccessible, certain calculations that couldn't be done. For example, the tangent line to a curve, a line that's tangent, as shown here. We have a line that's tangent to this circle and a line that's tangent to this curve at these points. Okay, well, in algebra, we know how to represent this circle or this curve with an equation, right? Given a center point and a radius, we can construct the equation of any circle. And then here, this would be like a function, some function of x. Okay, and we also know how to represent the equation of any line, right? That has a certain slope and goes through a certain point. Okay, but what if we were given a point on a circle like this, or a point on a general curve like this? So we were given these points, and we were asked to find the equation of the line that's tangent to the circle or curve at these points. Well, if you really think about it, if the only knowledge you had was a mastery of algebra, trigonometry, and geometry, you wouldn't be able to do this, okay? And that's actually what the derivative is all about. The derivative is all about being able to fully define tangent lines to curves at points on curves. Specifically, the derivative allows you to easily calculate the slope of a tangent line to a curve at any given point on that curve. But once you have a slope and a point, you have the full equation for the tangent line as well, right? Okay, and so it's kind of weird to think about, but that's literally it. That is all the derivative is about. It's about being able to easily determine slopes of tangent lines to curves at points, or if you extend this past single variable calculus, when you get to multivariable calculus, then you've got, a function of two input variables would be a surface in 3D, right? So if you're thinking about like a tangent to a surface, like a plane that's tangent to a surface, then you're wanting to easily calculate the slope of that plane, the equation of that plane. That's what the derivative is all about. That is it. Okay, but now what's important to note, though, is that you might think to yourself, well, what's the big deal? This can't be that hard, right? Like, so we're given the coordinates of these points. So we know exactly where these points are. Okay, and then we also have the corresponding curve that these points are on. We can draw in, we can visually see the tangent lines. And so we can just kind of get the slope of the line from the picture, right? Then we'll have a point and a slope and just write out the equation of the tangent line. Okay, and yes, that's true. You're right. And that's probably the way mathematicians, scientists, and engineers prior to calculus solved tangent line problems like this. It's not like prior to calculus being invented by Newton and Leibniz, no one had even thought about solving this type of problem. No, many mathematicians before Newton and Leibniz made contributions that laid the groundwork for the work of Newton and Leibniz. Okay, but what you can think about is that at some point, it really becomes necessary to have officially established rules for doing something like finding the equation of a tangent line to a curve at a point. So, okay, why is this necessary? Why are officially established rules necessary? Well, one reason is because the idea of drawing a line tangent to a curve on a page with like a graphic software and then estimating the slope, well, how do you know that you drew the perfect tangent line? And how are you estimating the slope? How accurate is your estimate for the slope? And I mean, what if you have people in different parts of the country or the world calculating these tangent line equations with different methods? Results could be different, right? But then furthermore, if you're using just arbitrary methods to solve these types of problems, then there's going to be holes and inconsistencies when it comes to trying to build off of these concepts. Or not even just build off the concepts, but maybe if you're solving two different problems, the nature of the problems are different. Okay, well, because the problems are different, you could get incompatible results if you're just using some arbitrary non-systematic method, right? That's the whole reason, like even algebra and trigonometry and geometry are built systematically the way they're built. It's so that there's a consistency among mathematicians in any part of the world, mathematicians and scientists and engineers, in the results that they get, so that there's no holes in these results, depending on the type of problem you're working on, right? It's kind of like any rules that you state for finding the equation of a tangent line, like the method for finding the equation of a tangent line. You can think about how these rules need to hold up in court. You can't have some math lawyer come in and break down the details and say, well, there's inconsistencies here. You state this here, but if this, and this happens, then all of a sudden what you stated doesn't make sense. That can't happen, right? So it really becomes necessary to establish an official mathematics that formally and systematically lays out how to answer these types of questions. And then from there, you can build off of these concepts. You can use these concepts as a solid foundation that has no holes or inconsistencies in it. Okay, and so that's why as you go through this playlist, if certain concepts or definitions seem trivial to you, that's the reason. Okay, it's because definitions and concepts need to be vividly and systematically laid out so that everything is bulletproof. There's no holes or inconsistencies anywhere. Okay, so it says in this section, we see how limits arise when we attempt to find the tangent to a curve or the velocity of an object. Okay, so the tangent problem. The word tangent is derived from the Latin word tangens, which means touching. Thus, a tangent to a curve is a line that touches the curve. Okay, but the issue with this definition, this meaning of the word tangent, is that, so as shown here, both of these lines, this line T and this line L, touch the curve at point P, right? But obviously this line L is not tangent to the curve C. Okay, but now we could say that line T is tangent to the curve C at point P, but really that statement would be purely visual. Because if you think about it more specifically, what we would be saying is that it looks as if line T is tangent to the curve at point P, right? Okay, so now it says for a circle, we could simply follow Euclid and say that a tangent is a line that intersects the circle once and only once, as shown in this figure. Okay, so if you're dealing with a circle, then a line is tangent to a circle if that line intersects the circle at just one point, right? If you have a line that intersects a circle at just one point, then that line must be tangent to the circle. Okay, so maybe we could extend that definition to not just a circle, but any curve. Well, that's not going to work because as shown here, line L intersects the curve C at just one point. But even furthermore, the line T that looks like it could be the tangent line intersects the curve at 2 points. Okay, so it's really this statement here that we're looking for in that. So, okay, in other words, a tangent line should have the same direction as the curve at the point of contact. It's a line that touches a curve at a point and has the same direction as the curve at that point of touching. Okay, but how can we represent this definition here mathematically? Okay, well, let's look at this example 1 here. We're going to look at the problem of trying to find a tangent line T to the parabola y equals x squared. Okay, so we want to find an equation of the tangent line to the parabola y equals x squared at the point P 1, 1. So 1, 1 is on the parabola. So what is the equation of the tangent line to this parabola at the point 1, 1 here. Okay, so we will be able to find an equation of the tangent line t as soon as we know its slope m. Yeah, because then we would have a point and a slope. The difficulty is that we know only one point P on T, whereas we need 2 points to compute the slope. Yeah, to get the slope, we need a second point. Okay, but observe that we can compute an approximation to the slope by choosing a nearby point Q on the parabola. So we're going to come ahead of point P, so with x greater than 1, and think about some point Q on the parabola that has a x coordinate given by x, some x greater than 1, and then a y coordinate given by x squared, which is the y of x, right? We're just leaving this in terms of x. It has an arbitrary location somewhere on the parabola. And again, we're just thinking about x being greater than 1, though. We're somewhere ahead of point P. Okay, and so now what we want to do is we want to think about what is the slope of the line that goes through point P and point Q. Okay, and what this line would be called is not a tangent line, but a secant line, meaning that it intersects a curve more than once. Okay, so the slope of this secant line, PQ, would be, you do, as we know from algebra, y2 minus y1, x squared minus 1, over x2 minus x1, x minus 1. There's the slope of the secant line PQ. Okay, and so it says, for instance, if point Q is at x is equal to 1.5, and therefore x squared is 2.25, the slope of the secant line is 2.5. Okay, and so now what they do next is they make a table here and determine the slope of this secant line for an array of different values, but specifically these values are getting closer and closer to 1. So 2, 1.5, 1.1, 1.01, 1.001. And if we track what the slope of the secant line is doing as we get closer to 1, well, it looks like the slope of the secant line is getting closer to 2, coming from above 2. Okay, and so it says this suggests that the slope of the tangent line t should be m is equal to 2. And really what they're saying here, when they say that this suggests that the slope of the tangent line should be equal to exactly 2, is you could think about how what this seems to be indicating is that if we had a really powerful calculator and we plugged in for this MPQ like a value like 1.000501 and looked at the result, it's going to be something like 2.000501. It seems as though as long as we plug in a value for x, this value could be very close to 1, extremely close to 1. With like an enormously powerful calculator, it would be very close to 1, but just above 1. 1.000, a million zeros, 1. This seems to be suggesting that the output we would see is something that's extremely close to 2, but just above 2. So like 2.000, a million zeros, 1. And so we can then think about, well, okay, if then hypothetically, x was equal to 1 in this equation, x was equal to 1 in this equation. I'm saying hypothetically because it can't actually be equal to 1 because we can't divide by 0, right? But this seems to be suggesting, this table here, that hypothetically, if from the perspective of this secant line, if x was equal to 1, then the slope would be equal to 2, exactly 2, right? Okay, and so that's the idea of a limit. We say that the slope of the tangent line is the limit of the slopes of the secant lines. And we express this symbolically by writing, we're saying that the slope of the tangent line to the curve y is equal to x squared at the point P11 is exactly equal to the limit as Q approaches P of this secant line formula MPQ. And that's equal to M, like the exact slope of the tangent line, the exact slope of the tangent line. So it's the limit as as point Q approaches point P of the slope of the line that connects point Q and point P. That is the slope of the line that's tangent to the curve y is equal to x squared at point P. And mathematically, what this means is that you've got the slope of the secant line in terms of x, and we're saying, okay, it's the limit as x approaches 1 of the slope of the secant line in terms of x. That's what we saw here. Okay, and they actually did this same analysis coming from the other direction. So we can extend this to think about, okay, well, what if Q is to the left of point P? Okay, well, they do a breakdown here. So x is approaching 1 from below 1, and you get the same result that you would expect in terms of the slope of the secant line is approaching 2, but from below. So this validates that in general, it seems to be the case that the slope of the tangent line to the curve y is equal to x squared at the point 1, 1, we could say is exactly equal to 2. And this is based on this idea of a limit that we just roughly introduced. So we haven't officially talked about exactly what limits mean yet, but we've just roughly stated that it seems to be the case that if you had some extremely powerful calculator that could work to, thousands of digits, thousands of decimal places, then if you, into this secant line slope formula, if you plugged in 1.00 1,000 zeros 1, then you would get, for the slope of the secant line, 2.00 1,000 zeros 1. And then also, if you plugged in 0.999 1,000 nines, then for the slope of the secant line, you would get something like 1.999 1,000 nines. To where it's like, okay, well, we can then hypothetically think about, well, if Q was sort of exactly at point P, right, which would be the actual tangent line, it wouldn't be a secant line anymore, then hypothetically, this MPQ would be equal to exactly 2. But you can see the need for the idea of the limit here. It's because we can't divide by 0, right? That's the problem. What we're really needing to do is we're to solve this tangent line problem here, we're needing to analyze how some function behaves, how something behaves when that function is very, very, very close to a certain point, almost infinitesimally close, but never actually at that point. That's the whole reason we're needing this idea of a limit here, okay? But again, note that we haven't stated anything officially here. It's saying, okay, assuming that the slope of the tangent line is indeed 2. So it seems to be that is the case, but we haven't made any official statement. It does look to be the case that the slope of the tangent line to y is equal to x squared at p is equal to 1, 1 is 2. Okay, but again, we haven't made any official statement yet. So assuming that the slope of the tangent line is indeed 2, well then, okay, now we have a point and a slope, and so we could just use the point slope form of the equation of a line, y minus y1 is equal to m times x minus x1 to get the slope of the tangent line. Y is equal to 2x minus 1. Okay, so figure 3 illustrates the limiting process that occurs in this example. As Q approaches P along the parabola, the corresponding secant lines rotate about P and approach the tangent line T. Yeah, and they go from both directions. So Q is above P. Here's the starting secant line. Here's the actual tangent line. As Q approaches P, that secant line approaches the tangent line, right? And same idea coming from below P, when Q comes below P. As Q gets closer, the secant line approaches the tangent line. Okay, many functions that occur in science are not described by explicit equations. They are defined by experimental data. The next example shows how to estimate the slope of the tangent line to the graph of such a function. So yeah, now we're just going to look at this from another perspective. So we're not thinking about the equation of a tangent line to a function at a point, or like an equation at a point. Like even a circle would be an equation, right? but we're thinking about experimental data. So it says the flash unit on a camera operates by storing charge on a capacitor and releasing it suddenly when the flash is set off. The data in the table describe the charge Q remaining on the capacitor, measured in microcoulombs, at time t, measured in seconds after the flash goes off. So we're starting off with 100 microcoulombs at time 0, and then as the flash goes off, here's the time elapsed since the flash was initiated. So it's not much time, right? Just overall, it's 0.1, a tenth of a second. And then here's the charge remaining in the capacitor at each of these times. So use the data to draw the graph of this function and estimate the slope of the tangent line at the point where t is equal to 0.04. Okay, so here they plot these different points and then connect the points with as smooth of a curve as possible. And so if we're thinking about what's the slope of the tangent line to the curve at this point, well, what they do is they say, okay, well, let's just calculate the slope of the line that connects point 1 and point 3. So that time 0 and time 0.04. So that would be the slope of this line. Okay, and so that's what they do. There's the point at 0.04, and there's the point at time 0, and there's the slope. y2 minus y1 over x2 minus x1. It's a negative slope, right? That makes sense. Okay, but now what they do next is they say that, so, okay, the point P was at time equal to 0.04. That's what we're trying to get the slope of the tangent line to the at this point. Okay, now point R was the other point we chose to calculate this slope. So here they just use all of the other points as point R. So this is the slope we just calculated, but they look at, okay, well, what if we used the point for time is equal to 0.02 and as point R, and then point P would be the time equal to 0.04. Same with time equal to 0.06, 0.08, 0.10. Okay, and it says from this table, we would expect the slope of the tangent line at t equal to 0.04 to lie somewhere between the t is equal to 0.02 and t is equal to 0.06 slopes. And so what they do is they average these two slopes. Okay, our arguably our best estimate and an improvement upon this initial estimate is this minus 674.75, the averaging of these two slopes. Okay, now another method it says is we could do this graphically. You could get a piece of graph paper and precisely plot these points and then connect the points with a smooth curve, then draw in the most visually accurate tangent line that you can, then construct a triangle and find the ratio of this length to this length. And that's what they do here, and they get minus 670 for the slope compared to this minus 674.75. Okay, so next they talk about the velocity problem. So what is the velocity problem? I thought I had mentioned that the only issues that derivatives solve are related to tangent lines, equations of tangent lines. So why are we talking about another problem in addition to the tangent problem? So the velocity problem is just viewing the tangent problem from another perspective. That's it. The tangent problem was a pure geometric viewpoint, or you could also say a pure algebraic viewpoint as well, because we make graphs in algebra. But the idea is you could think about how before calculus was invented, let's say someone was riding a horse. And actually, to make this easier to conceptualize, let's just think about a car driving down a road in town. Okay, imagine you have position versus time data for the car, a position versus time function for the car. Now, the car runs a red light, and when it runs the red light, the traffic camera takes a snapshot of the license plate as the car crosses through the intersection. So what if we also wanted to know the speed at which the car ran the red light. So the question would be that in that snapshot picture, how fast was the car going? Well, you can see how the question that's being asked here is about what we could describe as like the instantaneous velocity of the car, right? Instantaneous because it's a velocity at a moment in time based on that snapshot picture, the single moment in time. Well, before calculus, even if we had the position versus time function for the car, we would have no formal way of determining this velocity value. But with calculus, the idea is that the velocity at this moment in time would just be the slope of the tangent line to the position versus time curve at that time point when the snapshot picture was taken. So you can see how the velocity problem is just the tangent problem from another perspective. It's sort of like a real-world perspective of the tangent problem, you could say. And I don't know if I even want to say real-world problem, though, because, I mean, you could potentially have a real-world geometrical type problem involving a tangent line in actual space, right? So, but the velocity problem is just saying that before calculus, there was no way to officially determine the rate of change of one parameter with respect to another parameter at an instantaneous single point of the independent variable. Okay, and so but this is really not about velocity. Velocity is just being used as the main example. You could have any parameters. Maybe you have a revenue versus cost curve, right? Well, at a specific cost value, like an instantaneous cost value, what's the rate of change of revenue with respect to cost? Well, that would just be the slope of the line that's tangent to this curve at this point, whatever the slope of this line is. Okay, and we saw this perspective in example 1, right? The slope of the tangent line to this charge versus time curve at t is equal to 0.04 represents the rate of change of the charge in the capacitor with respect to time at t is equal to 0.4 seconds. Okay, so it says if you watch the speedometer of a car as you travel in city traffic, you see that the speed doesn't stay the same for very long. That is, the velocity of the car is not constant. We assume from watching the speedometer that the car has a definite velocity at each moment. But how is the instantaneous velocity defined? Let's investigate the example of a falling ball. So what they're saying is that if whenever you're driving in a vehicle, your speed is constantly changing, right? It's usually, in general, it's not just a constant velocity or a velocity that's changing linearly with time. If you plotted a position versus time graph of a vehicle, it would be a sort of nonlinear random curve in general, right? So how do we think about the idea of at a moment in time, what's the velocity of the vehicle? So, okay, suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, 450 meters above the ground. Find the velocity of the ball after 5 seconds. Okay, so through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time it has been falling. This model for free fall neglects air resistance. So yeah, this is what we learn in engineering dynamics. Okay, so if you have a free falling ball, then neglecting air resistance, you could model the position of the ball with a parabolic function like this. But even if you were including air resistance, you just have it would still be like a polynomial here. Okay, but the idea is they're saying at time t is equal to 0, the origin is at the top of the tower. So we could look at this another way. You could potentially say that at time t is equal to 0, the ball is at s is equal to 450, but they're just trying to keep it simple. Okay, the difficulty in finding the velocity after 5 seconds is that we are dealing with a single instant of time, right? They're not asking for like an average velocity between time 4 and time 6. No, they're saying what's the instantaneous velocity after 5 seconds. If you took a picture of the ball right at 5 seconds, there's the picture, and you want to write what its speed is on that picture, its velocity, then what would that speed be? Okay, so what we can do is we can estimate the desired quantity by computing the average velocity over the brief time interval of a tenth of a second of time from t is equal to 5 to t is equal to 5.1. Yeah, so we could potentially say, so here's the position function, right? We could say, okay, at time t is equal to 5, what's the position? Then at time t is equal to 5.1, what's the position? Then take that change in position and divide it by 0.1. So there's a good estimate of the speed at time t is equal to 5. And then so that's what they're illustrating here, but they take it even further. They do the position at time t is equal to 5 to t is equal to 5.01, that change in position divided by 0.01, and they take it even further, right? But what are they doing here, though? What are they doing here? This is exactly what we just did in regards to the tangent problem. Because you could take this position function, this s is equal to 4.9 t squared, and you could plot it, right? S versus t. All they're doing is, so at point P, which in this case is when t is equal to 5, they're just calculating the change in position between the position at time t is equal to 5 with respect to the position, this position q at time t is equal to something very, very close to 5, but above 5, and then dividing it by the change in the independent variable, the change in time. But they want to do this with, you want to hypothetically think about this with as small of a difference between p and q as possible. So you want to think about the limit as q approaches p. What does that slope approach? That's exactly what we just did. Except in this case, we don't care about the tangent line. We just care about the slope of the tangent line, the physical meaning of that as a velocity in this case, as a change in position with respect to time. And so it says, it appears that as we shorten the time period, the average velocity is becoming closer to 49 meters per second. And we could do the same thing coming from below. We could say, okay, take the change in position at time t is equal to 5 with respect to time t is equal to 4.99999, divide that by the 5 minus 4.999, whatever we chose, and see if that, it coming from below, we're also approaching 49. Or are we getting something like 48.99999 coming from below? And so it would appear that if we had some enormous calculator and we did this with 100 digits, thousands of digits of precision, that we would be getting something, it would continue to approach, get closer and closer and closer to 49, so that hypothetically, if we were thinking about the slope of the line in which q was actually at point P, hypothetically, because it has to be hypothetical because you can't divide by 0, we would expect that the slope of that line to be exactly equal to 49, which is we would say is the instantaneous velocity when t is equal to 5. Okay, but again, I want to stress, we're saying that it appears that this is the case. We haven't stated anything formally yet about like how exactly do limits work, right? If we're going to make a statement like this, how can we be sure that this statement is correct? Right now in this section, we're sort of just going through a thought exercise about how to approach answering questions related to tangent lines, equations of tangent lines. So the instantaneous velocity when t is equal to 5 is defined to be the limiting value of these average velocities over shorter and shorter time periods that start at t is equal to 5. Thus, it appears that the instantaneous velocity after 5 seconds is 49 meters per second. Okay, now you may have the feeling that the calculations used in solving this problem are very similar to those used earlier in this section to find tangents, and that's absolutely correct. It's the exact same concept. In fact, there is a close connection. It's not even close. It's the same concept to the tangent problem and the problem of finding velocities. In fact, there's a close connection, and it's not even close. It's the same thing, just a different perspective between the tangent problem and the problem of finding velocities. If we draw the graph of the distance function of the ball, as in figure 6, and we consider the points P and Q, yeah, that's what they're showing here. You could think about the velocity of the ball not just at t is equal to 5 seconds, but they're generalizing it. They're saying for any time A at which the ball is falling, okay, so that's what point P is, time A. Then if you go some distance ahead of A, h, distance in time h ahead of A, so now you have S evaluated at A and S evaluated at A plus h. So here's S of A and here's S of A plus h. Then you can actually evaluate S of A. So S of A is 4.9 A squared, and S of A plus H is 4.9 A plus H squared. And you can write out the equation of the slope of the secant line that goes through P and Q, as shown here, right? And this is the same as the average velocity over a time interval from A to A plus H. Therefore, the velocity at an instant in time, t is equal to A, is just the limit of these average velocities as h approaches 0, as h gets extremely close to 0. If we're thinking about an enormous computer that could calculate to thousands of digits of precision, then we could let h get extremely close to 0, then what would the resulting MPQ be? That's what we're saying is whatever that's going to be approaching something. We're going to continue to plug in smaller and smaller and smaller, closer and closer to 0 values of h. And we're going to be noticing that, okay, MPQ is getting closer and closer and closer to something. What's that something that it's getting closer and closer and closer to? That's what we're saying that we could potentially think about being the actual slope of the tangent line. But again, it's just a thought exercise right now, but that's what we're thinking. So examples 1 and 3 show that in order to solve tangent and velocity problems, we must be able to find limits. After studying methods for computing limits in the next 5 sections, we will return to the problems of finding tangents and velocities in section 2.7. Yeah, so we've in this section, we've just been introduced to how we could potentially think about this idea of a limit that will allow us to systematically solve these tangent and velocity problems. Okay, but we've just had a rough look at what the idea of a limit in this section. So what we need to do is, in the next 5 sections, we need to really break down what limits are. Officially, what is a limit? How does a limit work? And how do you calculate limits for all types of different functions and in all types of circumstances? Once we have a mastery, a thorough understanding of what a limit is and how it works, officially, systematically, then we're going to come back to the whole reason we started this in the first place. We'll come back to these tangent and velocity problems.